All right, guys, that was a great warm-up. Let's actually get started here. Emma, tell me something on number 1. What's going on here? Great. What do we call that? It is a vertical stretch. Amplitude. Nice job, Skylar. You get the next one. Wait, it's frozen, guys. You need to tell me if I'm writing and you don't see anything.
Oh, I didn't know you were writing.
I didn't know you were writing either.
Yeah, I wasn't. It didn't do anything. All right, so there's a 2. It's our amplitude. Skylar, tell me something else.
It died.
No, it's still there.
It's there. It's there.
It's plus 3.
It died.
It has a plus 3 at the end.
There we are. Go ahead, Skylar. So that's the b for the period. Awesome. So if period is 2 pi over b, which in this case is 2 pi over 2, that means our period is plain old pi. This means it's cycling twice as fast. Awesome. David, what about that plus 3? What does that do? Yeah, that shifts everything up 3. This is going to be our new midline, is at the line y equals 3. Good job. Okay, let's go to number 2. Tell me something, Brian.
The 1/2 is amplitude.
Yeah. So instead of stretching it, what is that 1/2 going to do? Louise, tell me something else.
The negative one moves it down.
Awesome. So now our midline is at y equals -1. And who can tell me what the plus pi, what is that going to do?
That's the B.
Awesome. We call that a phase shift. And it does the opposite. So since we're adding, we go to the left. Good job, Jade. All right, so this is some of our transformations. We need to understand these transformations because we're going to be writing equations that model real-life trig situations, okay? All right, so let's go to some examples of periodic data. Okay, if periodic data just means that it has a pattern that repeats itself. It goes through cycles. For example, it goes winter, spring. What? Well, you totally skipped summer.
Summer.
Winter, spring, summer, fall.
Well,
Then
it's just naming another season.
winter, spring, summer, fall, and it repeats itself over and over.
I like summer.
Sometimes Utah, we kind of switch things up and we get summer and winter and all of them all in one day, right?
Yeah.
Yep. Good old
Good old Utah.
season.
Now, even daily temperature here, guys. The daily temperature goes up and then down and up and down. And if you look at your phone and it tells you the hourly temperature, you'll notice it kind of makes curves like that. Where have we seen curves like this before?
In a sine?
What? Okay, now let's talk about this. Not all periodic data makes sine waves, but that's mainly what we're going to focus on. But even like this, your heart rate, you got your boop, 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 and then, what does that mean?
They died.
Okay, so, but is this an example of periodic data?
They're not dead.
It's repeating himself. It just means they got a crash cart and, okay, he's good. Let me show you two more quick videos
What
here.
is that one? The shiny light.
So, this one,
That isn't that. Look, wait. It's not. I want to say sound wave. Is it sound wave?
yeah, can you see this?
Is that our voices or is it just playing random stuff?
Up here, Skylar, you're going to get a new seat. Nelly, please don't be talking right
Is it talking? Is it
now. We need to be
saying
quiet
anything?
because listen to this. Oh, come on, it's got to be better
You're
now.
not
You
Let me
can
try
see
it.
it better on the tablet.
Whoa.
Do you see the sine wave?
Yeah.
Yes.
When we talk, it makes sound waves, and it's just a sine wave. And if you just focus on making one note, you can get a sine wave. And if your frequency goes up, like watch this, I'll try again. What happens is you've made the sound go up.
It gets higher.
It goes faster, right? Anyway, fun stuff there. Let me show you a quick video. This video, what they have here, before we start it, they've got a bunch of bowling balls, and they're all attached to cables, and they've got this beam that they're attached to on the top, and he's going to let go, and they're all going to start swinging. Now these ones up here, they have shorter strings, and then the string gets longer and longer and longer. And when they release, watch what happens. Let's play this thing. Play. And can you kind of see a cool pattern there? Ooh, what's it making?
Wiggly snake.
Yeah.
Sine wave.
Does that kind of make a sine wave?
Yeah.
Or a
Pretty
cosine.
cool.
Is this the thing where you don't get hit in the nose and you drop it?
That's a little bit different. But still, that involves a bowling ball on a string, right? But this is different. And if we kept watching, you'll see there's some cool moments here where, like, even though it looks kind of random now, that they actually follow a pattern. Like, wait a second. And you'll see, wait, there's still a pattern going on there where they get into clusters. See those clusters, and they're hitting at the same time so you can hear it. And then it kind of gets into the groups where they're still following a kind of pattern. Do you see that one there?
Yeah.
We don't have time to watch the whole thing right
Now
now.
it's
Maybe we'll watch it
DNA.
later. But it is pretty cool. So we see these periodic data in real life situations, and what we're going to focus on is how they apply to motion. Okay? Let me actually tell you one more story. One more story talking about this chart. So let me tell you a story about when my wife and I had our first baby. So my wife was pregnant. She was 9 months or so, and we knew that the day was coming where she'd start having contractions, okay? Now, you probably learned this in health class. When you have a contraction, does that mean you go to the hospital?
Yes.
You have to wait. Why do you have to wait?
Because it might be a fake contraction.
Yeah, they have Braxton Hicks contractions. So what a contraction is, if the guys were like, I wasn't paying attention in health class, the baby's in a uterus, and the uterus will contract, or kind of like, it's almost like a
Compress
cramp,
the baby.
okay? And it's like basically saying, time to get this baby out of here, so it squeezes, and then it releases, and that's called a contraction, okay? Now, if my wife started to have a contraction, and we're like, ooh, it's a contraction, that means maybe it's about time, and then, but you have to wait, and you have to wait until the contractions become regular, and at that point, that's when you go in, and they'll go and measure and see if you're good, and if you're good, then they'll hook you up to this machine, and this machine, it measures your contractions. So this is when the uterus contracts and then releases. It contracts and releases. And do you see how they're regular here? That they're following a pattern?
Yeah.
That's another example of periodic
Pattern
data.
of pain.
Now what's interesting here, this is actually the baby's heart rate, and you can see when it squeezes, what
The
happens to
baby
the baby's heart
dies.
rate? No, it doesn't die. But the heart rate does kind of go down. It's like, whoa, it's getting squishy in here, it's hard to breathe, and then it's like, okay, we're okay. And then, and basically, what's the goal? Basically, in the end, they squish the baby till it comes out. And then, hey, welcome to reality.
It
Okay.
seems like bad for the baby and for the mom.
Well, but that's kind of how it works. Okay. Now, I want you to think about a little kid on a swing. We're getting to springtime and people are going to parks more.
Well, technically, fall starts at like 7 in the morning. Spring's around
Yeah, we get a lot of
11.
the different seasons in a day.
Summer
It's
is
been raining
around
too much.
noon,
And then it goes
and then
down.
winter is like 7.
Alright, so what we're going to look at, guys, is imagine someone on a swing. And they go swing out, and they swing in. Swing out,
Are
and
they
swing
pumping
in.
their legs?
And they're pumping, but they're keeping a constant, okay?
Oh, that's pretty sad.
Now, what we're going to do is we're going to pretend we're looking above. So we're looking down. This is a person from above. And they're going to swing out and swing
Okay,
in.
so they'll
Swing
look
out
at the
and swing in.
x-axis.
But what we're going to do is we're going to let this represent time. So when I start my timer, it's going to actually carry that motion this way. So they're swinging
Okay.
out and then in, and then I say mark, get set, go. So they
Sine.
swing out,
It's gonna
and
be
then
a
in.
sine.
out, and then in, out, just like that. And
Wow.
yeah, what did we just make?
Sine.
Sine waves. So when we're modeling position, it can actually, we can model that using our sine waves. And that's what we're going to focus a lot on today. In particular, we're going to be focusing on that with a Ferris wheel. And I've got to get this to where people at home can see it. But here's our Ferris wheel. And we're going to do that same thing. The motor on this isn't that strong, but if we're looking at the height They can see it.
Maybe.
Like that.
Yeah, they can.
If we're looking at the height versus time here, this is kind of slow, but look at this. Okay, we're going to start a timer. And what we're going to do is measure the height. So we start now, it goes up, and then it starts to come down. It's halfway down. Then it goes down to the bottom, and then it's starting to come back up. Now, what am I slowly making here with my finger?
Cosine wave. Or, yeah.
A sine or a cosine. And we're going to learn you can actually do either to do that. All right?
But some ways are easier than others.
Okay, now how do I get out of full screen?
Escape.
I know
Stop
that.
it.
I know that, but it was the other way
I
around.
know, I hate when it's in tablet mode.
Okay,
We're all
watch
done.
this, guys. So this is from a little math website here. What they're going to do is better show you what I just tried to show you. What I tried to show you was how if we take a Ferris wheel and we model the height versus time, what we're doing over here we've got this red gondola, it's spinning around, and we're
Let's go
measuring its
back.
height versus time, and it makes a sine wave. But what we're going to do is talk about how we're going to adjust this. For example, if we make the amplitude bigger, it's a bigger Ferris wheel, what does that do to our sine wave?
It's bigger.
Makes it higher and lower like that. What if we decide to increase our period, or actually increase b, which makes a period go
We are
faster.
ejecting the passengers.
yeah, right here, could you imagine going on a Ferris wheel like that? Probably die, right?
That's
Now-
how you scare somebody who's afraid of heights.
If the
right
velocity
there.
goes too fast, then our bones or whatever can't take it and you die.
Yep. That's okay, we're not really going to do this. We can also shift it up and down and left and right. But the whole point that what I'm trying to get you to see here, let's slow that down a little bit, is that the motion of a Ferris wheel when modeled height versus time is going to make a sine wave. And what our goal is going to be is to come up with the equation that models that data. All right? Now we're going to see that. Let's move this now out of the way. With a couple of famous Ferris wheels. We're going to talk about the London Eye. For a time, this was the world's tallest Ferris wheel. Has anyone here been to London?
No.
That would have been cool. If you ever go, make sure you go on this. It gives you a great view. I'm going to ask Jade, will you read this for us? As she's reading, what I need you to be watching out for are some key details to help us graph to make the sine waves like what we just saw. So be paying attention to specific things that would help us graph it. Go ahead, Jade.
So, built in 1999, the London Eye was the world's largest Ferris wheel. It has a diameter of 120 meters, and at its highest point, it's 135 meters high. The attraction does not stop, but runs continuously at 30 minutes per revolution. Graph two revolutions of the lowest gondola and write an equation of a trigonometric function that models the height versus time of the gondola.
Awesome. So now when we're trying to graph the height versus time here, what are some key things that we probably need to remember?
It's a 30-minute ride.
It's diameter.
30-minute, yeah, when you sign up to go on this, you go in and you're on it for 30 minutes.
Wow, that line must be super, super long.
Yeah, I think what they do is they make you like pay in advance. You have to buy your tickets in
Oh, like
advance.
buy
You don't
your
just
spot.
show up. Okay, what else do we need to know when graphing this?
Diameter.
The diameter is 120.
And the highest point is
You need to know the radius.
Okay, now if the diameter is 120, what is a radius?
That's pretty hard math.
60.
Over.
60.
Okay, so now here's what we're going to do. This is on your paper, right? Let's
Yeah.
scroll down here and we're going to start graphing it, okay? So,
No, I have the Singapore flyer.
other paper then. That's your homework.
Okay.
So now let me graph a couple things. This said the highest point was 135. And it says the diameter, so the diameter is top to bottom, is 120. Now, how does that work? Why, if I go down 120, what's left over?
One.
15.
No, stop.
15.
It is 15. Now, why are we 15 off the ground? Why isn't the highest point 120?
So those poor gondolas don't scrape their little feet. off
There we
the
go.
floor.
We don't want them to crash, right? So we have a loading platform here, and you can kind of see that right here. There's this place where you go up the stairs and you get on it, okay? It has to be above the ground so that it doesn't hit the ground. Though I think it would be amazing if they made a Ferris wheel that part of it you got submerged under the water.
You would drown for 30
But
minutes.
no, you're in these like enclosed things. If they're like waterproof,
Yeah, but your motor can't even take it. It's a Lego man.
that's a
Imagine,
next one.
imagine if it had to fight the force of the water.
All right, now
It
what
breaks-
this
it's
is going to
not
do
rolled.
is it's going to start down here. You load at the bottom point because then you don't have to pay as much money to build it, right? And it says you're going to be done 30 minutes later. So at 30 minutes later, you've gone up and down, you're back to here. So by the way, let's measure. This is H for height, this is T for time, and we're measuring that in minutes.
Do you get 2 revolutions on this, or only one?
Yeah, we're going to do 2 revolutions. That means how long total is this going to be?
An hour long Ferris
16
ride?
minutes. They went on it once and they're like, let's do it again.
Why would you do that?
Because it
you-
gives you great
Do they
views.
give it to you twice? Like at like Lagoon, you get to go like 3 rounds.
Yeah, but that's because it's a lot smaller, a lot faster. These have got to be slower and more stable. Now, let's look at this first ride. If it's 30 minutes total, at what time are you at the highest point?
Halfway.
30,
Half of 30, which is
15.
15. So at 15 minutes, that's when you're at your highest point, which is 135. Okay, now when are you going to be halfway up / halfway down?
45?
About, yeah, about.
No?
Wait.
Just focus on the first trip around. So I get on it, and I'm going to go how long until I'm halfway to the top?
6.5.
No,
Close.
5.
What's half of 15? Thanks, Isaac, 7.5.
7.5.
Okay, and that means halfway down, let's just add 7.5 to 15, that's 22.5. Okay, now, I don't want you to shout this out, but I want you to work with your neighbor on this. What is the height if I'm halfway? Talk to your neighbor, and I want you to figure out what the midline here is going to be. Halfway between those, okay? Talk to a neighbor, figure it out. Go. How do you find halfway between 15 and 135? That's what you're thinking about, okay? Give you 10 more seconds till Antonio tells us how to do it. You got it right. Take the average.
I took the average.
what?
I don't think it's right.
Oscar, Antonio, did you come up with a way to do it? What'd you do, Oscar? You didn't do it. How do you find the average of 2 numbers, Oscar?
Well, we're not.
Shh. I'm asking Oscar. Go ahead. You're going to divide them after you add them. So let's add them together. What's 135 plus 15? And what's half of that?
75.
So our midline here is going to be
It's
75.
not. It's 60.
No. Now, Mindy's bringing up a good point here, okay? Oop, well, that's not what I wanted. Mindy's bringing up a good point here where she said the radius of this is 60. Because if the diameter is 120, half of that is 60, right? Well, that means from our lowest point, we should go up 60 to get to our midline. Is 15 plus 60, 75?
Yes.
Then we should go another 60 to get to the max. What does that mean 60 is going to be in our equation?
I don't know.
That's the distance from our midline to the max and min. What do we call that, guys? Amplitude is correct. Good
Well,
job.
I just did 15 plus 75, and then plus 75 it did equal 135. So I was like, that's not the midpoint.
So it is, you just got to check your math. So it's all right. Okay, so here we go. Let me graph one ride on this. So you get on, and then it's like, oh, let's go up. And then it's like, all right, and now we're going down. And that is one ride. And that's actually making a sine wave. That's one cycle of sine. And you said, that was so much fun. Let's do it again.
Like crazy people.
So now on the second ride, if it's between 30 and 60, what's halfway between 30 and 60?
A number that's halfway between 36. Is it 37.5?
If it was 15 before, just add 30. So let's take all these numbers we had and
25.
just add 30 halfway
That's all
between.
you're doing with it. That's easy. I knew that.
Then why didn't you say it?
because I thought we were doing the one between 30 and 45.
So basically, just take these numbers here and add 30 to them.
What is 45 plus 7.5?
52.5. So now we're going again, we said, hey, let's go. So then at the midpoint, we'll be halfway up at 37.5. We'll be all the way up at 45. And then halfway down here. And then back. And we're like, all right, that was good enough. I think we've seen London.
No, gotta get those 4-hour London right. I just fall asleep on it.
Okay, now, does that graph make sense? This is measuring the height versus the time for two trips. So it's saying you go on it, you go up, you get to the top, and you come down. You go on it, you get up, and then go back down. And you can see that that's making a sine or a cosine wave there, right? Now the trick is we need to come up with an equation that kind of models what's going on there. So to do that, we're going to use this formula at the top. Just like what you did with your warm-up, but now we're going to plug in the numbers. A, what does A stand for?
The
Amplitude, and you guys already told me that the amplitude, that's the distance from our midline up to the top and down to the bottom, which is 60.
Oh,
Do you guys see how, like, let me draw the midline in there a little bit better, okay? Here's my midline. And do you see how the distance from the midline to the max, or the distance from the midline down to the min? It's 60, so that means A is going to be 60. Now, what did we say the midline was?
75.
75. That goes right there.
Why is it
75?
K?
I thought you said 70.
K is your midline. That's so if you think about this, guys, sine waves normally start down here with the midline at 0. So
Oh,
I
yeah, I
shift
get it.
this
Okay, I got it,
up
yeah.
so the midline is now at 75. So if I add 75, that's how you make the new midline.
I got that.
Times the amplitude, make the amplitude 60 so that it stretches it. And now we've got to change the period. How long was a period? How long did it take for us to go through a cycle here?
2. Half 1. 2.
30 minutes, right? This ride was 30 minutes. So what we're going to do here is we're going to write the period is 30 minutes. So here's how I'm going to do this. Period is 2 pi over b. And we know that the period, or the length of one cycle, was 30 minutes. So I'm going to replace p with 30. Are you with me so far?
Yes.
Now we want to solve for b. It's in the denominator. How do we do that?
Multiply.
I'm going to switch the 30 and the b, right? I multiply b on both sides, divide by 30. I'm just showing you 2 steps in one. So that means b is equal to
What?
2 pi over 30.
Would it simplify that to 1 pi, so pi 15?
You sure can, and that's what we're going to do. So b is going to be pi over 15.
Pi 15. Oh, yeah.
And then is that.
So now when I come up to this, I'm going to put b as pi over 15.
What about H?
The last part of this is going to be the horizontal shift. And the reason why we have to do this is because when I look at this, does it look like a regular sine wave? When we're used to seeing sine, it starts at the midline. Like, let me just highlight one cycle here. This is, do you see that red highlighted one? This is what we're used to sine looking like when it starts. Well, that point is usually down here at 0, 0. It got shifted up 75 by the vertical shift. We already knew that. But how much did it get shifted to the right?
2 pi 4.
See that right there, 7.5? Let me show, like, this is how I visually think of this. I'm just going to go along the midline until I hit the graph, and then I'm going to drop down and say, how far was that? And that was 7.5. So that means it was horizontally shifted to the right 7.5
Do I have to do those
minutes.
double parentheses it has on there?
Yes. Oh, undo that. Come on now. So when I come up here, I'm going to put 7.5 right there. So let me show you, there's 2 ways we can write this out. One way is just like this. I'm going to put y is equal to, our amplitude is 60 sine pi 15ths gives us a 30-minute period. We had to shift it to the right 7.5, so I subtract 7.5.